All right, hello everyone. Welcome to another episode of Amplifying FSharp. Let me share the screen real quick. So, as usual, our little introduction. What is Amplifying FSharp? It is basically an initiative where we're trying to get more and more people involved in contributing to open source software. Start there. All right. The clue is that we do a weekly stream, or we definitely aspire to, where we touch upon various topics of the FSharp ecosystem, be it the compiler, be it tooling. We just try to have various topics. And last week's topic was about a compiler warning, where an object is inferred as a type. So we had Patrick on the show, where he was working on an existing pull requests, and we just covered some ground there. The PR got some more checkboxes ticked, so definitely great to see that Patrick is quote unquote unblocked and can continue his investigation for his contribution. So it's very nice to see. We are still looking for new topics for Amplifying FSharp. We have still a couple of spare sessions or topics to talk about, but this is really about what you would like to see on stream. Whether you're a newcomer or still need to learn, or a maintainer that just wants to showcase his projects to draw in more people, the point is that you can fill in this forum, tell us who you are, what your time zone is, kind of the topic you want to talk about, and just submit it. Whether you want to talk yourself or just want to have somebody talk about that topic, we'll try and get the right people in the group, and we'll try and organize things. Today, we're going to talk about signature files with a tool called Telplin. Telplin is a very recent tool, and it's an alternative take on generating signature files based on your implementation file. We'll quickly go over how Telplin is structured and perhaps do some coding later on, depends. And our guest for today is actually me. So I'm Florian. I don't really, I'm not a strange face or anything, so let's just skip introductions and formalities. Let's go with it. And yes, I am passionate about signature files. So, little recap for somebody who has never even heard of a signature file. What actually is it? Well, on the left, we have some FSharp code here. And a signature file is basically a way to tell everything that's inside a file that's actually the public representation of it. So it's basically a bit of a hash of what your code actually does and what the really relevant bits are. For example, the implementation of our function here is actually not listed. All it listed is that it returns an integer and it takes a time span. So whether we can generate these files, and Telplin is already a bit of a different take when you compare it to how the FSharp compiler generates them. Let me showcase that real quick. So this is a online tool. All good projects have an online tool. This basically just invokes the Telplin in a AWS Lambda. The slight difference between it is that everything is prefixed in the FSharp compiler, while Telplin will actually open your namespace, and that was like the biggest driver to start creating this tool. And we'll go over some other technical details of where the differences actually are. You might be wondering, well, if I have a signature file, isn't that like double bookkeeping? And to answer that question, yes, it totally is. So you'll need to provide the same information left and right for your codes to compile. That might be a major letdown for you, or definitely a turnoff to start using signature files. I won't try and push anything on you, but I definitely find them helpful. A signature file is typically a lot smaller than your implementation file, and it could contain your triple/ comments, which you only need to write on the signature end, and you can still get the IntelliSense tooltips for the usage on the other side. So I basically like signature files because you can just read a signature file, get the documentation, see what this actually does without getting lost in all the implementation details. Telplin itself has also some documentation, a little bit on the usage. It's actually a tool you're meant to install globally. Telplin really only works well for the initial signature file creation. Once you have signature files, there's no real story attached to it to keep them in sync. You can, of course, always regenerate the signature file. But there's a bit of a technical overview, but I'll just quickly mention the motivation. So why, again, would you use signature files? They help in the creation of reference assemblies. When you create a reference assembly, you also generate something that's called an MVIT. Or that's at least how I pronounce it. An MVIT basically is a hash that contains the public API of your assembly, of your reference assembly. Long story short, when the MVIT changes, it means your reference assembly is different, and there currently is an ongoing effort to stabilize the MVIT generation even more. But if you use signature files, the chances that things are stable are going to be more stable over time, or already a lot higher, because it's basically going to use the information from the signature file, and it doesn't bother with every potential detail in the implementation. Another reason why you would use signature files is because you can speed things up in the compiler. So again, a signature file basically is just a TLDR of what your implementation module is actually doing. So if you need IntelliSense for file D in this chain, in the IDE can basically just look into the signature files, skip all the implementation files, and then get your IntelliSense for file D, because type checking has a little gimmick where it can sort of skip the implementation because it already has the info from the signature. And another interesting feature we covered in this Amplify of Sharp series is graph-based checking. So bits, the same story. The signature file contains the information and can basically unblock all the rest of the dependencies within a graph to speed up type checking in parallelization as well. So there is a way to generate signature files using the all6 flag. I'll showcase that in a bit. And the biggest complaint I have about this is that for example, here, the code you have, there are definitely details that are going to be lost. For example, it's slightly outdated, but everything is prefixed, so that's one little annoyance. But then certain things are just kind of lost, like this literal warning when you're compiling it and then using it, a bit later on. So the literal warning over here was actually just transformed as a string because the compiler doesn't know that this was literal, and Telplin was able to detect these things. And I guess my biggest frustration with the all6 feature flag is that it's part of the compiler. The compiler needs to ship with a .NET SDK. So when you fix anything in the compiler, to my personal opinion, it takes forever until you get your fix available in SDK. That's not a nightly. And Telplin is just an online tool. So we can just .NET tool update it and start using the new version of it. All right. So let's maybe start with generating some signature files using the FSharp compiler. I went away and cloned FSHTTP, which is just a new project that doesn't have any signature files with perfect candidates. I don't really know what the code does, but I basically just need a FSharp project. The way you would do it to generate the signature files is to add an additional compiler flag. Now, the FSharp compiler it will be invoked by MS-build, and you can actually point some thing called other flags to add in additional compiler flags. So let's first add something that is --sig and then a file name. So let's say signatures.txt, because sig will actually just dump everything from the project into the file that we give it. So when we now do a .NET build, and let's just put the verbosity on normal so we can see the compiler arguments. So we see here it's going to invoke core compile. This is a target when your .NET build is executing. And when we see this core compile, we should see our --sig somewhere over here. Yes, --sig signatures, which created this file. And this is just a dump really of all the information of all the signatures to a separate file. So it's not extremely useful. Then there's even a slightly more convenient way to work with this. And that would be to use all6. Now, all6 is another flag where if we build this now again, it will generate all the signature files for us. If we look at this FSharp over here and then open this to the sides to sort of see what the equivalent is, we'll notice that, well, like I mentioned, there are no open statements and everything is in there. And maybe this will compile, but we're not entirely sure. So we still need to add the signature files to the FSproj. So if maybe out of curiosity, just add one real quick. See if it still builds. And unfortunately, we already have a bit of a problem. The generated signature file didn't work, so something went wrong. It's telling us that the signature specifies something else than the module over here, than the implementation file. So, that's one thing. And then we can report this bug if we're able to sort of pin it down to a small reproducible sample. We can report this to the FSharp team. But yeah, they actually have bigger fish to fry, and it is, it is tedious to get everything right over here. And if we had a fix, for example, for this problem, it potentially, well, will take until the August release before we have this. So that's a little bit of the downside of where the old 6 compiler flag turns in. Now, what we also can do to generate the signature files is use Telplin. Now, let me just real quick remove all the files, restore everything, and just invoke my local Telplin. So I have installed Telplin as just a shortcut for the local executable. You would just typically install it as a .NET tool. And what you can basically give Telplin as an input is the path, so the FSharp projects, or you can create a binary log. The twist is that you need the core compile target to be part of the log, or a response file. And let's maybe first create a response file just to talk a little bit about that as well. When we invoke Telplin with a FSproj, it is first going to build that FSproj. Then it's going to build it, create a binary log, and basically scrape the compiler arguments into a response file, because it needs the response file to get all the correct data for the type checking to be able to happen. So we're going to type check in Telplin using the FSharp.Compiler.Service NuGet package. And to perfectly do that, we need the exact same arguments that are being used to build it. So this is well, in my opinion, a neat little thing where you can say to Telplin, Telplin only records. So instead, we're not really going to be overly worried about creating a file. We're just going to point it to an FSproj, and we're going to record the arguments that are in here. So these are all the compiler arguments that you could use. And you're actually able to pass these arguments, this file, along to, say, a local compiler. So I also happen to have the local compiler in my path, which is called FCS. Let's also just put in the help. So you can see the local compiler. It's in my case in the FSharp artifacts bin. That's just where my FSharp repository was checked out. And what we can do over here is actually use that file. We need to prefix it with an @ so it knows it is a file that should be processed. Sorry, that it's an argument pointing to a file that should be processed. And when we then invoke our local compiler using the response file, it's actually just going to do the same thing as it does using, well, it's the same thing that MS build were to do if it doesn't build, but it doesn't have all the magic of doing restores and some of the other resolution stuff. So it is really interesting to sort of test out your own local compiler on things. And even if you're never going to use signature files, Telplin just really is quite interesting for that. It does, it's not really clever. So Telplin will actually just build your file and then scrape all the arguments from the core compile target by the binary log. A nicer way to do this would be to do a design time builds, but I'm just going to easily admit that I'm not clever enough for the design time builds and all its intricacies. So I just am pretty okay with creating an actual build that could be a reliable scrape file. All right, good.
One second, Florian.
Yes.
There's a little bit of concern about the audio quality. Could you check if you're using the big microphone or the
I
laptop
am using
one?
the big microphone. There's just a noisy neighbor here. That's not my control.
Okay.
Yeah, I was aware of that. Should be better over time, I hope. But yes, sorry.
Okay.
Good. So before creating your own tool, you should always try and ask yourself, is there a way to improve the existing tool, or why are we in the situation we are today? And let's take a look at what actually happens when you do all 6 from the compiler code base. So I'm just naively going to look for all 6 because I don't know by heart where all the stuff is, but I can notice that there is a compiler option called all 6, and that's going to be somewhere in the FSharp.Compiler.Service project. So basically, SIG and allsig are going to be processed over here, and we'll look a bit further for where this is actually happening. So this is going to add the compiler, and it's going to use the set all signature function, which has like a print all signature files. So again, without fully understanding what's happening, that I don't feel it matters that much, but we can just point to the next thing and try and see where this is set to true. So set all is being true. So where is this now invoked? It is going to be passed into an member, and then a driver, which is part of the FSharp compiler project. There, the flag is going to be used, and it's going to write a interface file. So signature and interface are kind of synonyms from time to time, and the write interface file will create something that's called a display environment. And that display environment will be used in the nice layout in the nice print function, which takes the type tree and tries to construct code again. Now, the thing with the display environment, and it's being created and adds a little bit of additional parameters. And the thing it also has is a set open path, where it basically says, oh, I've seen this open path, so every name that's being resolved can actually be shortened down because I've already seen a certain open path. For example, if you have a open system, this could be added to the display environment, and then every type that's from the system namespace could, doesn't need to be fully prefixed because we already know system. And the reason this isn't really set for everything that's present in the file is that we only use the type tree information and lost all the finer details of the untyped tree. I'll talk about untyped tree and type tree in a little bit, but the display environment is being created. And then if we go back to the code, it's being passed on into niceprint. And niceprint is a module inside the compiler. And again, the compiler is actually full of signature files. So that's also very interesting. I typically just look at the signature file and then see what is this all about. When you're lucky, there are some code comments. But basically, this is going to take a module or a namespace, and it's going to try and lay out the implied signature. The layout is basically a sort of objects tree model that can later be converted to text, which is what happens at the end. So basically, we're going to create a layout. We're going to squash it to a certain size, and then the show will take the node structure and create a string out of it. And if we go back to niceprint to the actual implementation, we just follow along, and then we see that we're having module or namespace contents as the last argument, as the expression over here, and that's basically like the top level thing, and that could contain bindings or type definitions, and these are then via some other helper functions being transformed into text. This is very, it's very good, but the type tree loses a lot of information of how things originally were in the untyped tree. And that's sort of where Telplin has a bit of a different approach. It will actually start using the untyped tree. To better understand how Telplin sort of operates, I have a little example here in the Fantomas Online tool. So we're just going to look at our source codes over here. And if we look at the AST, which is loading right here, we'll be able to see what's kind of in here. So there is a module or namespace. There is an open module. It's an open statement, sorry. There's a let binding, and basically those are the main parts. And what we can do there is just traverse this tree and try and reuse what we actually need. Because when we want to convert a correct signature for this, what we actually are after is a V of time span, and that also takes another, well, in this case, V is going to be generic, and is going to return an integer. Now, the integer, we know it because it's hard-coded right here, but that's really where your type tree comes in, where your code is going to be inferred. And basically, if we convert this, let's say it's a signature, then that gives us an equivalent tree, but notice that this time it is a SIG file. And to have a better understanding of what all these exact modes are, we can also use the expanded mode in the tool. It's a recent addition, which will basically prefix everything that's out of there. So we can now see it is a parsed input and a SIG file, and it will basically create a SIG declaration, which has a value and has all this good stuff. And that's basically the signature counterpart. So we're going to walk the tree and go, from the implementation to the signature. And if we have those, we can actually pass a syntax tree to Fantomas programmatically and create source code based out of that. Now, there's one drawback from the untyped tree here is that, well, it contains a lot of things Fantomas doesn't really need, and it's not that fun to work with. So what we are going to do is, instead of the AST, we're going to use the oak. Well, let me just switch over back to the implementation real quick. And then the oak, you can see, well, the tree is a lot shorter. And we can see that we, inside of an oak, when I now flip to the signature file, you can see that the oak just still is an oak. So the node module is actually exactly the same, because they just share too many elements, from what Fantomas really needs to know, that we don't make the distinction between whether it's implementation or it is signature. So this allows for a bit of a mix, and it also allows just to reuse a lot of things from the existing implementation to the oak. Sorry, to the signature file. So basically, we take the oak, we can take the module in the namespace, we can take the open list because, well, they're equivalents. And then the moment, in the case of a let binding, the moment we see a top level binding, we basically need to convert that to a val node. Yes, we basically need to create this binding node and create the val node to eventually pass this to Fantomas and create our actual source code again, our signature source code. Of course, the untyped tree alone isn't sufficient to detect all the types, so we will need the type tree at some point, and we will need to figure out, like, what is this B, or if there's something more complex happening in the body and there's no return type, well, what actually is it? And we're going to use the symbols from the type tree to do that. Let's briefly jump into some codes. And I have Telplin open over here. Before we start, I do want to come clean. Telplin actually takes a source dependency as of today on the FSharp.Compiler. I typically try to, well, when improving Telplin, I do try to improve the FSharp.Compiler, because then both methods sort of benefit from it. So I don't really try and fix everything in Telplin. I try to fix as much as on the compiler side, so it benefits everybody. And the way I typically do that is just by contributing to the main branch, and then the main branch gets merged to the 77 branch, which is the next Visual Studio release. and they actually make NuGet packages of that. Now I'm here at the .NET F# README. There's a link with versions that brings you to some TFS artifacts, and the latest version is from June 2nd. I had a fix in a little bit later than that, so I wanted to use that fix. So long story short, I'm basically cloning the compiler to a very specific branch, to a very specific commit that has all the good stuff in there that I need. And instead of using the NuGet package, which I could reference, I'm just ahead of the curve, and I'm trying to work with the latest and greatest. And I basically just reference this project in my directory props. I'm just going to reference my locally built compiler, but I am pretty much using the FSharp.Compiler.Service as DLL. And we're going to go over to see how that works. Telplin is also very unit test friendly. So let's maybe just jump into like a test. We have a simple binding test where we just know this is the implementation, this is the matching signature. It's first just going to match this and see, okay, is our expectation, is the string equal to what we expect? And then it's going to use the type tree to sort of verify, it's going to verify with the compiler that the combination of these two files actually produce a valid binary as well. Now, what we can do is debug this in a minute. But more or less our entry point will be the untyped tree function has a make signature file where we first go to get our incoming implementation code. We're going to make an AST out of that. That is using the Fantomas.Core compiler, so that's slightly different than the actual FSharp.Compiler.Service. I'll get to that, why that happens. We basically create our AST, we transform it to an oak. And then we're going to traverse that oak and go over all the different elements. And over here, maybe it's another breakpoint. When we go over the module in the namespace, we basically just go over the declarations and then just copy the header because the header is going to be exactly the same. And then we take the declarations. Declarations sometimes don't need to be in the signature file. So that's where we have this decl results. So either it's not applicable, or one thing in the implementation has a one matching signature file, or there is a nested module which has its own little things, and which could have errors. So we do try and do a little bit of error recovery. Like if one function cannot be transformed to the correct value, we do try and cover that and try and produce as much as possible. Because this is one of those things that people typically underestimate. Telplin just tries to do everything in the F# language, and that's very hard to get right. There will always be edge cases, and you really cannot think of everything up front. So it improves over time as it is used, but I do want to keep the code as straightforward as possible. And in our case, we're going to, the single let binding is going to hit this branch. So we're going to see that it's a top level binding. And then we basically want to create the val counterpart. To really figure out what the return type of the val is, we're going to use something that's called the resolver. And the resolver is a function that takes actually the type tree. So it's going to take the check results. So let me quickly go back to the previous file. We get the resolver already here. We already have it here. Let's see where it's being created. So I think this is a good spot.
Sorry, Florian, to interrupt you. We have a question in YouTube. Will you be able to answer it?
Maybe.
Or do you want to wait for the end?
Well, the first question definitely was answered. So
I pasted in the chat of.
yes, I'm looking at the chat question. So yeah, IDE performance will be better. I talked about that when I explained the one of the motivations in the documentation. So let me just quickly go back to that. So as in the motivation, the background speed up. This is the setting that's being used in IDEs for the FSharp checker to skip the type checking of the implementation file. Does that answer the question, or is there still some confusion?
Any IDE that uses the FSharp compiler service will benefit
Name me one IDE that doesn't use the FSharp compiler service. I dare you.
So yeah, the answer is yes, it will be. It will be.
Yes, it will be. So basically, the FSharp compiler service, the NuGet package, really is the heart of everything. So it is the compiler shipped as a NuGet package, and you're able to access things that happen during the regular compilation of your .NET builds. And one of these is type checking, which we're going to see in a little bit. And the checker, the FSharp checker is being created to do that. And all IDEs use the checker. So it's definitely, yeah, sorry for skipping over that little bit. But
one case where it does not, or where Ionide will not use the signature files, and that is to support analyzers. And since Ionide is the only one that has FSharp analyzers built in, to properly use them, we can't actually do signature file or use a signature file for diagnostic reports, since we rely on the diagnostics to feed into the analyzers.
That's kind of interesting. I don't really see why you don't get the diagnostics.
Because generally when you're doing like the type checking, it's only going to check the signature file, and you're not going to actually check the implementation. So it's for the analyzer.
Yes, well, it sort of depends. You could type check the entire project, and then you definitely should also have the results of the implementation files. So I guess it's a little bit of how that works. When you check the individual file, you want the flag to be off, so it really checks all the files to get that dependency point. But yeah, definitely an interesting thing. So it's jumping around a little bit in code, and I'm trying to get to the good stuff where it's actually going to create a resolver, which is just a bit of a helper class that first has the type check. So we have a checker over here, and for testing, I'm creating a in-memory checker. I'm not really passing in any special flags here, except for the document source. There is a way to use the FSharp checker, but don't read all the files from disk. You can basically tell the checker how it should load files in the project when it needs the contents. And I have a little helper function over here that will basically grab something from concurrent dictionary, return iSource text, which is an abstraction over the file content. So your editor could read your file from disk and do that like once, but then keep using in-memory versions. And that's one nice little thing. It's definitely for unit tests. The fact that we can do this all in memory, I don't need to write every example to disk and then read it back. That's a wonderful little improvement. And this basically creates a FSharp checker. The FSharp checker will be the heart of the entry points, so to speak, of your FSharp compiler adventures. The checker here has actually the public API, more or less, of what you can do. And a couple of interesting things. For example, you can check a file in a project. You can parse and check an entire project. Right here, we're going to parse and check a file in a project, which actually makes me wonder whether I really need the parsing. We could just do check. So that's actually a nice to do. But basically, it needs project options as well. And the project options are more or less everything, that it needs to know about your project. And that's is exactly what we did with the response file over here. So all the project arguments are just these guys. And it's going to wrap that in a project options, where most of these are just going to be other options, and the actual files will be stored as files. But then the project options over here, in this case, I created a bit of a default project options just for testing. But when you run Telplin from the command line, it's going to construct a FSharp option that really matches, your actual project. So it's going to have your project name, your source file, other options. And these are the things it really needs to eventually build all the type check information. So it's going to make the resolver. When it does that, it is going to type check the file. So we give it a type check, we need the source text, and we give it the project options, and we get a FSharp check file answer. Now, the answer could be that it was aborted because your editor could potentially, start type checking, but something else happened, and then you just want to stop it, and then you want to type check again, and all those wonderful fun scenarios. So we're never really hitting this, but it could happen. And when we succeed at type checking the file, we basically are going to include all the check results into the resolver. And if we then later on want to get specific information, which we're going to do here, about a certain symbol, we can use the get symbol used as location to really identify what's the type information of the text and the range that I'm passing along here. So we'll debug this in a moment, and it's going to be a lot more sensible. But once we have that, we can actually extract the signature text. And I propose we just debug this to see this in action. But then we're going to talk about display contexts again. So let's go back to the tests. If we were to debug this, we basically don't know what B is yet. We don't know what the entire A return type of A is. And we can see here that this is the test API. It's going to basically verify. It's first going to type check the implementation, because you shouldn't, try and get a signature file from invalid code. Then if that worked, it's going to try and make the signature. When making the signature, we notice that the code is coming in. We're going to create the AST. We're then going to create the oak. And once we have the oak, we're going to just reverse it. We have the module definition, which is the top level binding. And when we go over there, for example, we get the name. If we look at the name should be A. So that has text A. And then we're going to ask the resolver, give us the value text for the name. And get file text is a very recent addition to the FSharp compiler. You won't find this in any public NuGet package just yet. So this is only a bit of a week old, but I find it to be very helpful for Telplin, where it's basically going to grab the symbol first. And you can see here, we're looking for a symbol of A. We give the end range of A. We also need to pass in the source line, because that's just how the API works. So we try and find a symbol use, and a symbol use is a bit of a abstraction, where the symbol use sort of has the symbol, and the symbol itself could be multiple things. And in this case, we're interested if the FSharp is a member or function or value, because that's more or less what we're after. We're after the typed information of that text. And if we then look, we found a val A. And that's really going to have all the information that we're after, which you will see that curry parameter groups, it has a parameter B, for example. We can sort of drill in and try and find out what is B, what is the type. We can see the type is an int. So all this good stuff really is in there. And another interesting thing is what we're going to see here. It also has the display context. And the display context will well, in this example, not really contain anything, but it would contain the information of any open statements that it already processed. So it's not applicable for this first test, but let's circle back to it when we have an open statement. And basically what this get file text is going to give us, it's going to give us the, well, what do you expect it would do? It's giving us the string or the actual text that we need for the signature. So in this case, when we want to have a signature of A, that's the little snippet we need. And then we return that, then we're going to parse the text basically again with Fantomas, so that we have nodes again to work with. We're basically going to make another oak just based on the text that we have. So this little text, we just don't want to insert it as if, we want to create an oak again. And so we have the oak, we're expecting the oak to have just a single declaration, which now has a node. And the results of this was okay. So we have a signature node, and that's the one we really want to insert later on into creation of the counterpart val node. This file node has the correct type parameters, for example, or it will have the return type. And that's really what we are after. And there are a couple of things that, is just reusable from the untyped tree. And for example, the documentation or attributes or some of the other flags, we can just reuse them as is. And what that really helps is the thing that we would have when there are open statements involved. So let's try and look for an example where that's the case. Okay, for example, daytime now. Going back to the online tool, let's take another look over here at the online tool. So we're going to see that just a second. Yes, so we see that Telplin just copied the open statements and that FCF did not do it, so it needed to prefix the daytime. And when we debug this text, we'll see that there's actually a difference in our display context. So the display context will at least have these two open namespaces when we go to that point. So it found a symbol use, and when we look at the symbol use over here, we see in the display context, and it should resemble something over here that tells us the opens. Exactly, yeah, this is the collections, and it seems to have that for multiple things. Not really sure why that's the case. But the fact that it does have that, it's able to really chop off every leading namespace of a type, and that's what gives us this nice results. So going back to this new API, that might also be interesting to just go over. It's nothing mind-blowing, but it's just interesting if you're a little bit involved in a compiler and know where stuff is, then it's great to do proposals that maybe the FSharp team doesn't need themselves, but are useful for the community. And let me just try and find the definition. So there's a public API for the get signature, and let's go to the implementation. When we go to the implementation, this doesn't do super much, but it basically just gets the display context and it needs the range. And it will just see what this is. So the FSharp value or member or function or binding is one of these internal DUs. And we can just go back into nice prints. Should probably, maybe can debug that, not really sure. It goes back to nice print, which is all internal kitchen, but if you just expose it in a nice API, then we can reuse what is out there already, what's working really well for the compiler. So there are a lot of things that the compiler does well, but the limitation of just having the all six is again the empty display environment. But we don't have an empty display environment. In this case, it is populated because we asked a symbol very specifically to where we are, and the fact that we copied all the open statements to the signature file means that we have all the same information available. So that's going to work out. And if we do have that, then we can just piggyback on the existing goodness of the compiler and get that back in. So maybe debug one more time and see if we can get in there. So we might be able to, because I have a compiler locally, this might actually work, that we go into the codes of what's happening there. No. Or I should press F7 instead. So one more time. Yes, cool. So it's going to check whether it's resolved. And then we see the display environment. It's a additional flag. And maybe this is going to work. There we go. So we can see that our value A, in this case, has internally D, which is a value B, the cryptic DU. But again, this is internal kitchen, so they're allowed to use names like that. This is not exposed, so it should be fine, right? And basically, we can see that we can now piggyback on the existing code. And okay, it's a little cumbersome to debug, but it is a third-party NuGet library, so we typically don't debug those that often. But you can see there's a whole lot of more information available in this internal nice print than there is in the symbols API, for good reason, because you would well, you don't want to expose too much of an implementation details in the symbols API. But there's more information over here. So the fact that we can use this and leverage this to create good signatures, this is really helpful. All right. So there's a couple of things in the chat. I see a Tom at the end, so I'm assuming it's all good. And I see a slightly confirming Edgar, so it's gonna, it looks fine.
All controlled in the chat now.
Wonderful, thank you, my friends. So yeah, that's good stuff. That's also more or less what I wanted to tell about Telplin. Maybe just to wrap up, let's do a little bit of coding on something new. So Telplin does have bugs. You can use this report issue button and just then, well, depending on what tab you are on. So maybe the problem is with Telplin itself, and then the red button here opens a issue template in Telplin. So over here, report issue goes to, well, my repo Telplin, or, well, this is just exposing what the FSharp.Compiler does. So this does the generate signature, the same thing as happened in command line. And if you did find an issue over here, I made a button that sort of links you directly to .NET FSharp, which you can also just report issues in a, well, slightly convenient way. But yeah, a couple of issues do exist, unfortunately. And maybe one interesting one that we can take a look at is the non-comparable structs. So I'm really not an expert on structs or a wizard or anything, but I noticed that if you have a struct that takes an object, it no longer implements IComparable. And if you were this to be an int, then it would still have IComparable, which is something I guess you don't overly think about when you use structs, depending on whether you're really going to compare them or not. Maybe that's totally not the goal. But the warning of the compiler is really only available when you put your warning level on 5. 5 is probably the verbosest you can go. So this code is okay, but the underlying problem doesn't really surface to you. The compiler knows that this doesn't use IComparable anymore, but as long as your own code doesn't really affect that, then it's it's not going to raise it. Unfortunately, when you create the signature file and it's just created as is, this is not going to be a match because the signature file sort of indicates, oh, this is a struct, but it's not comparable. The code is slightly different, and I think it doesn't do the check whether the constructor really has the interface. So the fact that I think the problem is twofolded. So it either should do like a better job at checking the new constructor in the signature. If that is part of the struct and it's using non-structy things, then it should just give you a warning because it's not comparable. But for this demo, I was thinking, what if we just slap on the no comparison attribute and call it a day? Because that might be slightly easier. Now, the thing that would be new is to verify from the symbol information, can we somehow figure out that this type is or is not comparable? So that's one of the things maybe to wrap up that we can take a look at. Let's first go to a file type test, which is like a good fitting file. I have this test template. I believe by FSharp. And let's maybe create two structs over here. So I want the implementation in this case. Let's create two structs, see one that is comparable and one that isn't, and then see is there like a way we could have detected this. Let's just call this X. And that's struct and
Florian, can I answer? Can I answer a question? I don't know. Can I ask a question?
Oh, definitely.
Yeah. I mean, so another way could have been to say, okay, you annotate the struct declaration in your FSE with the icomparable interface, but is that not possible because you do not have the information, or which part of the FSharp compiler actually decides these implicit implementations like icomparable or equatable and so on?
To the top of my mind, I don't really know where exactly that happened. I would assume it happens on both sides of the story, like the implementation side will see that this has this object, and I guess does the check and does not add the interface. And here the signature side probably doesn't do the same check, so that might be one problem. So the workaround, of course, if this was your production code, you should just be honest about it and put in the no comparison attribute, because that's the right thing to do. There we go. And I'm guessing it just happens in the type check code for both. So if we circle back to the compiler, I would assume this check happens somewhere in checking over here, where it's going to check the declarations. That will be my guess. That's somewhere in here when it checks the type. So check one implementation file. So this is going to type check all the stuff, and then somewhere here it is going to, in one of the various phases of the type checking, it is going to assign the interfaces.
Yeah, but exactly, they have to be there, otherwise you could not correctly type check. But it's basically. Now you need this opt out. I mean, you have to opt out. It's not enough to not have the interface. You have to opt out in order to tell the users, hey, there's could probably something not as you expected. That's the thing, and you don't have this opt out information in the compiler.
Well, actually, you have it, but when you even don't use signature files, you really need to put in a certain flag until you can sort of draw it out. Let's actually try that. So this is non-scripted stuff, but let's create a test file over here. Let's put in the thing, open system, and let's now just call our local compiler and pass it in the script file. No, don't do PNGs. So over here, test, there we go. So it's trying to compile this. It gives you a warning, but it actually didn't give you a warning of a certain kind, which if we now put on the warn level to 5, by default it's 3 or 4, I think. it should, oh no, sorry, say no comparison. It should really tell us that this isn't allowed. Just double check what I'm missing here.
You have this struct attribute you do not have.
Correct.
Yes.
Yes, exactly. Thank you. So yes, this is a warning, which you don't get if we were not to put in the warn over here. So this says it's all fine, except that it's empty. But this is, saying that the struct record or union type is not comparable because of the objects, and consider adding no comparison. But from the signature point of view, this check isn't really a warning. The signature is going to assume, because you have a struct, that it does implement comparable. So in order to satisfy the signature, it should at least have the no comparison.
Yeah.
And that's sort of the mismatch that we're seeing right here.
And I mean, just for me to understand. So, for example, the warning that is generated when you are on warning level 5. Yeah. How are these warnings represented? I mean, are they part of that type representation, or is it just a one-shot computation that is then added to some warning array or whatever?
They're actually, so when you have the file and check results, they're going to be part of the diagnostics over here.
Yeah. But it's not part of the type definition. So you do not have this information directly related to that part. It's more like delocalized. Do you understand what my question is? Maybe
a little less, but I'll debug and show you the diagnostics, and it it should be in here depending on our log level. So we're able to see that programmatically. That's what.
And then you have also a link to the type representation. I mean, so that there must be some code model in the F# compiler that represents the type you are writing there. Yeah, and you somehow you can understand.
Yes, the diagnostic will not be linked to the type tree node, for example. It's only, it's going to be in this file at this position, this happened.
Okay.
And yes, it's not going to exactly tell you on a like node level, this is wrong with the nodes. It's I guess what you meant localized there.
So it's hard to reuse this information when you're doing such stuff that you're doing now, because you cannot really understand that this information is related to this.
Well, that's actually a very interesting thing, because we could try and pinpoint the range of the error to the untyped tree range again and say, oh, this is actually a part of that. And if that does happen, then we probably want to put in the struct attribute by default. But that will be more or less the other way around than I had in mind. Yeah. But it is kind of interesting. Let me just really take a note out of that.
Okay, this connection would be more like a guessing or a good guess, but not a real hard, reliable information. Then probably.
Well, it's going to be pretty reliable. Because when you let's take the level 5 warning again, it gives you it at 5.6, which probably is the start column of our little thing here. So it's 5.6. So I guess that's more or less going to be this location. So it does tell you for the start of this name, and I guess we could put the warn level on 5, then see for this range, is there any diagnostic that starts like that has that number, and if it does, then we should just automatically add a struct. That's one way of doing it. But of course, why not? Let's just try that. I have something else in mind, but it doesn't really. It's kind of fun to explore now. Let's go to the type tree. So we use the in-memory checker, and we also use like some pre-made fixed type tree options for the unit tests. So when we over here, when we make the resolver, we had the project options, but that's actually there's a make for codes, and we get those options. We get those options from here, and options. Yes, so these are just some hard-coded options that are, sensible defaults, and there's a set of resolved assemblies which points to a specific folder where I added some reference assemblies so that most types are present. So that's easy if you just want to use a sample that has like a system namespace or system collections, that all that stuff is available. And what we could do here, we put our warn on 5 so that we draw out the problem. And then let's just take a look at our breakpoint that we had and see if that's now being hit. So to be quick, but over here, going to yes, diagnostics. So we should hit all that. Let me remove some stuff. Okay, one more time. I missed it. So it didn't try to get file text, which is really weird. Maybe it didn't compile. Yeah. It's not hitting anything at all. Yes, which actually makes sense, because the symbol is resolved a little bit different for constructors. So there's a get file text over here, but there's also a get file text for constructor. There's a slight difference, and we basically want to have a symbol that has the compiled name of .ctor. That's like an internal little detail, but that's a good way to distinguish that that's really the symbol we're after. So let's maybe try and compile it like this. Sorry, put our breakpoint over here. Could not compile source implementation file. That is correct. What did we mess up? Would be fine. Yes, now I know. So this is really good stuff, kids. It now came into this code path because I believe the diagnostics will be checked up front, and if there are any warnings, then we're not really going to compile yet, which is a bit of a chicken and egg situation. So let's try and see where that actually all happens. Let's try and go to the code where we first do the implementation type check results. And I assume that this is the point I'm going to hit. Probably the splits. So it now has the one single diagnostic. And so this is not structurally comparable at the no comparison. And let's just maybe ignore this check for now, just to move the plot along. And now we're making a signature file. So the check results of A also has the diagnostic. And diagnostic has a range. So that's range 12.6. And the range we're now asking for the compiler is actually very close. One might sort of compare this range with this range and say, oh, that's actually exactly the same range. There's a little one-off, but I think that is because the F# diagnostics are 1-based and the FCS ranges are 0-based. So we could just do the plus one-off and then say that this is the problem. So if we have this check, then we should, I guess, return it. So we'll need to return a slight different definition, or just accept the string. We also let's just return a rule whether we need to add the attribute or not. Just for now, we might want to do something a little bit cleaner later on. Now we try and go to the implementation, which is no longer valid, and let's say needs structs needs no comparison. And that will be diagnostics array that exists. The diagnostics have it has some sort of codes, I think. Array
Error number.
Yeah, it's kind of weird that it's so the error number, this one. And well, it's start line would be equal to the range dot start line, and the diagnostic start column should be the range start column and then +1. And if this is the case, let's just return that. So file text says okay here. All right, well, let's see where this is used. We're lucky, it's only one place. Fiddling. So the file text and needs attributes. And we're going to so a lot of things could go wrong. Like if we don't find a symbol, that's why we use with the result type. If we cannot parse whatever the signature was from the compiler service, that's why we also do the result thing. So basically, we're just going to map our way through this and say val node, and then just return the val node and its attributes. It should be fine. And boy, okay, this is slightly more difficult. We probably want to do something slightly different, because this is a little bit too focused on returning a member definition and not really having any link to the type, or not that much to the type. So let's just roll that back. and come up with a slightly different approach. And let's say needs no comparison attribute. And then we just give it a range and get a rulback, and we'll just move that logic a little bit. It's going to be slightly more easy to deal with. So let's say member range. We can most likely just turn this. Yep, there we go. Right. So it is being used at the moment we create the type definition. And so the type definition itself has a type name. So type name really is everything related to it. And it already has a bit of a check whether it needs an additional attribute. So we could just well, we just sort of extend that a little bit, and using the attributes over here. So sometimes an additional attribute is needed for seal or class interface, because there again is not enough information returned in the untyped tree to work with. And we're going to so yeah, basically do our call maybe here and ignore most of the existing code. Let's just do that again. Attributes. If resolver dot needs no comparison, then we should be able to put in, I guess, the type name. So it comes from the, I guess, implicit constructor. Type definition type name identifier, that's most likely it. The dot range dot FCS range. So even though the untyped tree of Fantomas looks exactly like the one from FCS, it's definitely its own assembly, and yeah, it has the same types with a different namespace. So that's where there are little helper functions to convert this to an actual FCS namespace. And if that is the case, then we are going to see attributes as an option. So let's say match the existing option. If it didn't have any, and let's just create this. And there's also some, I guess, stuff in here that we were able to use. Note class attribute. So this is just basically, a way to create an attribute using the oak tree model. So I'm just gonna copy that and say, comparison real quick. Go. And otherwise, if you already had an attribute, let's do this. And let's return the already attribute nodes. So it's kind of depends whether there already were attributes in there. So yeah, it's a bit of a mix between if there already are attributes, then this can't be the case. So we can safely do this. So attributes are combined. So you could do something like foo bar, and then there's an attribute list, which contains two attributes, foo and bar. So in this case, we kind of know if there are no attributes, this is the first attribute of the type. So let's just do it like that. And no comparison attributes already is a list. So probably, yes, that's why. So don't overly worry about these type of details. Not all that relevant. We're just basically constructing something from the previous. So attributes is a attribute list node. So yeah, I really should use the online tool and don't do the blinds to get a better idea of what I'm actually doing. But attribute list, not attribute list. List nodes. Okay, so that was that, and this. All right. Of course. Yes, more or less. Okay, good. So we'll double check if it needs the attribute. It's going to create one here. It's going to check, did it already have attributes? Try and merge it in with the existing attributes. In our case, that's not going to count. It's good at this point. And then we should have the additional attribute in the type test. Let's just debug that real quick. And, so this is null for the first and also for the second. So that didn't totally work. The breakpoints in the actual method. There's one diagnostic. It has the right error text. Part-wise 12 and for range is 12, 5. Start with 5. Wonderful. So it does use internally, diagnostics do use 0 ranges, but when they print it to the screen, they probably make 1 ranges out of it, is my guess right now. So and then of course we do need a actual results. Let's just quickly grab that from the tool. Because we didn't really match our expectations yet. So this is definitely the error. So the signature, this check doesn't really look into should it be no comparable. There's just definitely something wrong in the compiler as well. And this is going to, I think, do it like this. No, because in the untyped tree, we are shoving it before the existing attributes. So I think this should be it. Okay, so it does have attributes, and then it's going to no comparison and the existing attribute. Existing attribute in this case should be struct itself. Try and double check that real quick. Attributes. Type name. Struct, okay. And it could not compile the signature file, so that's definitely another problem. But it did do the right thing here. Now it could not compile the signature. Let's briefly look into why that is happening. And the verification results has one additional yes, so this is a bit misleading, but the problem we're seeing here is in the implementation file in the FS, and it's actually the problem we ignored before, so we need to ignore it again when it does signature verification. Maybe to wrap up, let's go into to see how that code looks like. We are basically going to type check both files in a project, so the signature and the implementation. We're going to use the in-memory checker, but over here, this is going to produce a diagnostic, and it is going to yield both the diagnostics from the implementation file and the signature file. So in this case, let's just, ignore that diagnostic for now as well. And if we run this again, I would expect that this now passes. And there we go. All right, that's a very interesting idea, Ronald, to sort of try and piece those things together. But unfortunately, we did have to manually figure it out. So it's not part of the type tree or the symbol. The symbol doesn't, I think, reflect any diagnostics. They all just happen at like the top level of the file.
No, so I think for it, all the signature file was before really hidden or really depending on the compiler, and now we are starting to see all of these, cases where there's not the signature file doesn't match the implementation based on the compiler, because we are now more with the new with the improvements in F#. This is going to be more visible, I guess. So.
Yeah, definitely. So ever since the graph-based type checking, it is really apparent that there were things that are broken with signature files for years. And, because of the less common use, I guess not that many people use signature files. So it's kind of understandable that the F# team doesn't really, pick up every little issue that signature files have. But nevertheless, that's why we're here. It's not impossible to fix something on signature level, like nice prints. Once you get the hang of it, it's definitely worth solving. And yeah, we can definitely tackle some of these things ourselves and try and get better tooling for signature files.
Good question, Florian. So how do you see, or would you see these signature file generation working any IDE where you can have maybe an option to say, generate your signature file based on the file that you are, or your implementation file. Can you see that? Can you envision that in terms of being something that can be done?
Yes, that probably is doable. So depending on the IDE, they might have slightly different ways of using it or doing it. I think the only real easy use case I would see is FSAutoComplete, because there it could just shell out to Telplin, give all the compiler options. So the response file, the flag, FSharp.Autocomplete has all these settings. So we could easily pass those or just easily write them temporarily to disk. Say that the file, lives there. Say we want to have the signature for a certain file, and then just shell out and create the signature and be done with it. That's definitely one of the more easier ways to sort of do it. I guess Visual Studio Writer could do the same thing, but then again, yeah, it's maybe a little less likely, and they probably have their own philosophy to use this. So in pure of actually using Telplin, maybe not every IDE would be on board with that, but that's not really the ultimate goal of Telplin. That there's like no real world domination plan attached to this, but it definitely is a interesting project, and it inspires to fix the compiler, because there are a lot of things that, if you think about it, or if you try and move forward with signature files, and there are a lot of options today, similar to like the val text API. That was a very recent thing, and it surfaced because of the experiments Telplin is. So I definitely do encourage people to try it out, even if it's just to report bugs or gaps that are currently in the compiler side. And yeah, I do think that there's a lot of value in having such a tool.
Okay. Thank you.
Just as a FYI, I do have a work in progress branch for FSAutoComplete to use Telplin to generate signature files.
Oh, Jimmy, how long have you been keeping that a secret?
I don't know. I got to basically like the critical mass of like, hey, this thing works. But the hard part then is just actually like, how do we actually want to distribute it? Do we want to do the same thing where we shell out, or because like right now I'm doing like a direct reference to it, and so the rework to shelling out wouldn't be too difficult. But I do have the I think the harder parts come down to like, because like I can generate a signature file from a regular file. That's pretty straightforward. The interesting thing there is then getting into how do I keep things in sync properly? And that's gonna be like a lot harder. Like, do I want to say like have a code fix that says like, hey, this thing isn't exposed. You want to add it to your file and then just add that single thing.
Yes, well, and that's really where the val text API comes in. That's what my ambition was, to add the single thing to the type tree. So the val text, if you do get the symbol that's not in your signature file right now, and then just get the val text and insert that into the signature file, you should be done. And for FSAutoComplete, it could be hopefully very easy to spin up and then insert it. And if the signature no longer matches, I hope you can. I'm not really sure actually. I hope you can also just get the signature from the type tree, from the implementation file, and update the given range that's no longer in sync, and then so that it's perfect again. And that's where this val text is actually surprisingly good at representing what's possible. But it, of course, all hinges on, are your same open statements, are those in sync in your signature values or no, because of the display environments.
I have to admit I have never used signature files, and so because this synchronization, I mean, it's a one-shot thing, and then you really have to maintain it. That was the problem. The first thing I tried to use, but then I said, okay, it just hinders me. It just slows down my pace. Yeah, but maybe that was also in the phase where my project was too volatile. So I don't know where's the sweet spot. The sweet spot to kick it in. Yeah.
One of the sweet spots, in my opinion, is when you have a file like this, which is about 800 lines, give or take, and the signature is just one little thing, one function, and that sort of, doesn't change often. And if you're in that kind of situation, this really speeds up compilation because it can, just do all the type checking on a separate thread because of the signature file. And if it doesn't change that often, that's really the interesting bit. And also documentation wise, I don't need to go through all these code and understand what it does. I can just check, oh, this is the only relevant thing. It takes a resolver and some code and it returns a string and it's a list of errors. So that's, yeah. Okay, granted it misses a / comment here to add some more finesse to it, but yeah, it's already, just the trimmed down TLDR version of this file. So
yeah, interesting. So you don't need to go to the content of the function or to understand what it's going to return. If it doesn't have a type of annotation, then the compiler will need to go all the way through down just to get what's the end result.
Yeah.
Yeah, you don't want, like, when you're still like exploring a lot and messing around, don't use the signature file for sure.
Yeah.
But once you there's a couple cases, like, yeah, you have giant files that really only expose like a couple public methods and they've been settled. Like, some files you look at and you're like, when's the last time you touched that? It's like, if it's been like 6 months, it's probably a good case for a signature file. Like, there's no reason not to have it. And then also it's just like your solution is rather large and you want to have better, snappier type checking. And there's previous sessions that we've had about our graph-based or the graph-based stuff that's coming in the compiler, and the signature files really help with that as well.
I guess if you're really serious about your code and if you're like enterprise level, then, it makes a lot of sense that you have signature files as well. Just for the newcomer documentation, and it makes you reason a lot more like, should all of this really be exposed?
Yeah, exactly. Yeah, so I want to ask, so when you have a signature file, is it necessary to document or to have all the definitions of your public API in the signature file, or is it optional?
My recommendation is to just have all the definitions in the signature file. So when I hover over this implementation, it says good stuff. And that's because I just added good stuff over here. So it keeps it in sync on every possible way that you would hover over this, regardless of where you are. If it's in the signature file, you'll be able to see it. So at the point it's being used, I can also see good stuff. So you really only need one place for documentation.
But you do not have to have it in the signature file. It would also work to have one definition in the signature file and the rest of the public API is still not in the signature file, and it would compile. Or does it change the behavior that once you have a signature file, you have to have all the public parts of your API in that signature file?
Yes, well, you would. So for example, if I add a new file over here, even if it's let public very on the nose, this will not be public, even though it's listed public. The fact that it's not in the signature file doesn't make it public. I cannot, go over here and say untyped writer .a. It's not there. I mean, it has to be in the signature file before it's available.
Okay. Yeah.
And that's a bit of the downside, but at the same time, I don't need to use the private keywords to keep A outside of the IntelliSense of this file. So
I would not call that necessarily a downside. I mean, it can also be an advantage. Yeah. So it's
definitely. It's but yeah,
gate gate.
It's a topic of controversy within the community. I think I definitely like them, but not everybody's on my side in that.
Yeah, it's again, it comes down to the volatility of the code, right? Like if it's not that volatile, it's great. Like I don't see a downside to it. If you are messing with that file a lot, there's a lot of volatility. Like, it's good. It's just kind of also just a separate question of just like, why is that code so volatile, or so on and so forth. But when you're trying to get things done, that question isn't something you want to ask.
Yeah. It's also maybe really cool to detect breaking changes. I mean, on type level, but which probably always happens that breaking changes on type level.
If you have like an assembly with a public API, then I do recommend like the last file may contain your public API. Put a signature in front of that. And you know, the moment you touch the signature, you actually know that you're breaking your API. So
yeah,
that's you know, might not be required for everything internal, but it really does help you when you really do think about the boundaries of the file. So it's it tends to grow on you. That's maybe my closing words there. All right, I think we're out of questions, so let's maybe just wrap up the live stream over here and just stay for some more chat afterwards.
Could you give us a teaser, maybe what's coming next week, just so we can.
Ooh, would there be a teaser for next week? On the next episode of Amplifying FSharp, we are actually having the one and only Petter from the FSharp team to talk about Visual Studio tooling. So we're going to have Petter, who's one of the new people that joined in the proc team, who's gonna go through all the little bits and pieces of the FSharp tooling, which is in the same repository as the compiler, which is the way Visual Studio interacts with everything. So it's definitely going to be an interesting session next week. Join us at 2 p.m. So a little bit
in the chat to Suki, which contribute to the FSharp compiler, sorry, the Visual Studio. So yeah, that was really good to see.
Thanks, guys.
So that's it. Thank you, guys.
all right, cool. So let's all do the fake wave thing, and then I'll just try to find the stop screen button.